Welcome to the Gridwise Architecture Council's video library. The following presentation by Yashar Kenarangui of Xcel Energy is entitled Connecting the Dots Between Grid Modernization and Virtual Power Plants and was presented to the Gridwise Architecture Council on October 16, 2024. Welcome, Yashar.
Thanks, Jamie. My name is Yashar Kenarangui, and as Jamie indicated, I'm a principal engineer at Xcel Energy. Been here for 3 years and working in the emerging technologies group, kind of looking at different technologies, evaluating different technologies, doing techno-economic studies, and really kind of assessing the technology readiness of various aspects of the technology, but also, looking at the people and processes too, because technology readiness is one thing, but when you're trying to adapt and implement technologies at a utility scale, it's much more than just the technology itself. Been in the industry for 13 years now, mostly prior to Xcel Energy, mostly, consulting and analytics, power system analytics, and basically working in engineering firms. So with that, I can basically start my presentation. So I decided to basically start more basic and foundational with my presentation. There's a lot of talk about virtual power plants, and they come in different flavors. And there's also a lot of things that are happening in grid modernization fronts, and kind of trying to see how we can connect the dots between grid modernization efforts and a new thing called virtual power plants. Just an important note that this presentation is not a commentary on Xcel Energy's strategy or plans. Okay, so to understand where we're going, we need to understand where we were. So looking at the past decade or so, the way we've been running the distribution system was pretty much unidirectional power flow from these large power plants, and we've all heard the story, basically, doing forecasting, coming up with these worst case, peak demands and building our grid around that, and operating the grid, based on reacting to contingencies and maintenance is pretty much, kind of responding to, fatigue and failures, and with not much analytics and, proactive measures until starting now. And looking at the trends, we're seeing and expect to see more demand from electrification of loads, including EVs, but more basic things like heating with heat pumps, as well as a lot of customers are adapting renewable energy and energy storage for various reasons, being environmentally conscious citizens, as well as trying to, gain some resiliency against outages and self-generation. But there's also large developers that are connecting into the system with the economic objectives. So we're seeing a lot of, DERs in our distribution systems, and they're causing several issues, reverse power overloads at the substation and at feederhead breakers, to causing some issues during reconfiguration scenarios where we have to disconnect them. So we're seeing, some of that happening in our systems. Also, we're seeing a lot more stakeholders than before. Before it was just the customer and the utility, and customers expected a certain level of reliability with affordable rates. But right now, as customers are adapting more and more resources, they also expect to know more about their basically their consumption, as well as expect to get compensated for their services. There's also third-party aggregators that are entering the power grid, such as various OEM aggregators, and they have access to hundreds of millions of devices that they can aggregate and play into the markets. So the power system is basically becoming more complex, and little by little, we are realizing that we need enhanced and new approaches to plan and operate the future system. Where we are today is a question. We are under a massive transformation, but each utility and each region is a little bit different. A lot of utilities have adopted advanced distribution management system (ADMS), and they're working on various, distributed intelligence applications for EV detection or various applications at the grid edge. And these technologies are emerging, but making a blanket statement in where each utility is difficult. But a lot of things are happening today at various utilities and regions. So a few challenges and opportunities that we see in planning and operating the grid today. So I've kind of divided this into really 3 steps. One is, we're trying to basically interconnect as much renewable energy resources as possible. So typically at utilities, there's DER interconnection group where with each application, they study the interconnection, the resource capacity, nameplate capacity, and do these studies to make sure that the interconnection of these resources are not going to cause grid safety and reliability. And as the capacity of the grid is reached, we're looking at different new solutions to allow the customers to interconnect their devices, given the current capacity of the grid without with reduced or avoided interconnection costs. Because typically when customers connect, the concept of a cost causer, right? Whoever basically hits that capacity limit, they have to pay for the upgrades in order for them to basically interconnect. But there are new concepts such as flexible interconnection, which is being presented as a solution to allow the customer to interconnect, because most of the time the constraint is during a very isolated period of the year, maybe few percent of the year. So if we can avoid those constrained times, we can allow the customer to interconnect, but the customer has to agree to be curtailed or limited generation, and that requires a new interconnection agreements. So this two blocks basically is telling us, we're trying to transition to clean energy by allowing more renewable generation and storage to connect. But then, as we're reaching the grid capacity and as we're expecting significant load from electrification to connect into our systems, we have to rethink DER. And instead of seeing DERs as detriment to our systems, we have to kind of see how we can use DER as asset into the distribution system. And that goes beyond interconnection and enters into integration. So how can we integrate DER into the distribution system and use DER to basically have more robust system? For example, the non-wires alternatives are being presented as a solution to basically trade upgrading of a substation to maybe installing a battery system at the substation for those constrained times. And those solutions might be economic. It just depends on the scenario. And so there's a lot of opportunities for us to use DERs in the future planning and operation of the system. And that we're hoping that is going to basically lead to reduced cost for end-use customers. So with these new goals that we have in operating them and planning the system, we need new functions. A few examples, key examples are improved visibility. AMI data is being used today to get insight into what's behind the meter in terms of, um, electrified loads that customers are adapting. Also, getting a clue, real time or near real time clue into the loading on service transformers. And that can be used either for operational use cases or maintenance use cases, as well as sophisticated analytical tools for planning. As I mentioned, mostly we've used these snapshot type of calculations that look at peak conditions, but now because of the complex power flows, we really need to look more widely into the operation of the grid. So we're moving towards more time series um, uh, types of power flow calculations. And eventually we have to kind of think about how we can dynamically operate the grid, because set and forget type of operation is going to hit its limits with the expected increase in electrified load and DER. So we have to kind of think about new planning and operational paradigms to run our grid in the near future. So now we've kind of discussed some of the needs we have in terms of new functions that we are planning to implement. But when we talk about the technology, we have to kind of view the technology as a building, because there's a lot of technology out there, and just kind of adapting technology in an ad hoc manner and connecting things together is not going to work. And in fact, it might make our grid less reliable than in the past. So we have to have a strategy around building functions and capability um, in our systems. And typically, people talk about crawl, walk, run approach, because one step approach kind of overlooks at the complexity of the problem. So we have to take one step at a time, and we have to um, make sure that each step serves as a stepping stone or a platform for additional functionalities and capabilities. And I was kind of thinking about like how these capabilities are evolving, and I came up with this kind of visual. We're really starting with the interface between the grid um, and the customer, right? And IEEE 1547 is playing a significant role in defining the roles and responsibilities and interaction of the grid and the customer. So things like power controllers or power plants are playing a significant role to kind of aggregate customers' resources and present it as one controllable unit with respect to the grid. So in order for us to kind of interact with the customer's DER, we also need a DER gateway device, which houses several key functionalities. It serves as communication, um, basically translation, communication protocol translation function, as well as fail-safe controls and some cybersecurity provisions to be able to securely interconnect with customers' device. We're also leveraging the point of interconnection device, not just as a protection, but also a fail-safe device that if the schedule is violated, basically the local controls can disconnect the DR and prevent grid impacts. So this is where almost all utilities have some capabilities, and as I mentioned, a lot of utilities also are adapting advanced distribution management systems, which basically goes one level higher and implements a central control for supervisory control and data acquisition. And advanced ADMS also houses as operated model and state estimation, and it allows the operators and grid engineers to observe the grid in real time, even in those locations that we don't have equipment and sensors. So the concept of DERMS is basically built on top of DMS. So with ADMS, um, most of the devices that the grid operators are interfacing with are grid assets typically owned by the utility. But with the more and more adoption of DRs by customers, we see the need to gain visibility and coordination capability with customer resources. So this is a little bit of a paradigm shift because now we have to reach to customer devices, right? And we do that in several ways. We can use a secure DER gateway devices as an interface point. Typically, that's used for larger scale DRs, but with small scale DRs, we're still relying on OEM aggregators or third party aggregators to establish that communication and interoperability with the end devices. So with that, let's jump into VPPs. We've heard that term a lot. I was looking for a simple definition of a virtual power plant, and I think this is a good one. It's an aggregation of decentralized energy resources managed collectively through smart technologies to mimic a traditional power plant, enhancing grid stability and flexibility. So there's not a set definition for VPPs today, but the concept is interesting. So to look into VPPs, we can start by considering the characteristics of a traditional power plant. A traditional power plant like a nuclear power plant or a coal or a combined cycle, these are large installations, very investment intensive, and mostly sited around lakes for cooling. And their sole purpose is to basically generate and inject power into the grid. And they provide several key services such as energy, capacity, and ancillary services with very well-defined performances. So basically, VPPs are trying to mimic same um, same device configuration as large power plants by aggregating a whole bunch of customer-owned devices, and these can be in tens of thousands and millions. And the devices that we're talking about are basically regular, equipment that customers use, such as thermostats, water heaters, um, but also, more and more electric vehicles, as well as energy storage and PVs. And not to mention, a lot of the large industrial installation also have on-site generation that can also be leveraged. So it's all about aggregating small scale DRs in bulk to be able to get similar characteristics from them. However, there are challenges, right? Because the primary use case for these devices is the customer. Customer uses HVAC to keep their home warm or cold. And, customer uses its energy storage energy for resiliency purposes, as well as EV's primary use case is for transportation. So we're aggregating these devices, the customer comfort level and customer use case cannot be compromised. So that's one constraint. The second constraint is, the communication link. We're primarily reliant on internet-based communication, which can be, um, less performance than SCADA type of communication. And like for example, customer Wi-Fi can go out, and that basically reduces performance. Also, these devices, other than energy storage, they have much lower performance than your energy storage systems. And another maybe challenge is cybersecurity. Because we're increasing the attack surface by introducing cloud-based solutions with interconnection through internet-based communication systems. So there's a lot of R&D that's going on to kind of mitigate and work on these challenges, and there are great results. And it seems like, there's a great potential for VPPs. Obviously, we have to start by implementing simpler use cases and not expect the same performance, but, they are capable of meeting some of the distribution and transmission use cases that we envision. Last thing I would mention is that VPPs should serve both the bulk power system and distribution system. It has basically, it needs to have the capability to serve both, as we will delve more into this in the next slide. So the VPPs, basically are applied to the grid, and one thing that's important is meeting the needs of the grid, customer, and market simultaneously. As I mentioned before, the distribution grid operator, for the most part, has been monitoring and controlling the grid assets. But with DR aggregators, coming into play, they can aggregate customer resources to independently participate in grid services. However, their service might cause distribution grid violations. For example, if aggregator is grouping a whole bunch of behind the meter energy storage systems, that can potentially overload the service transformer. So both these things need to be considered together. So the distribution needs and reliability has to be met as the aggregators are participating in these systems. So that's basically highlights the fact that the distribution grid operator needs to be in the loop as the aggregators are providing grid services. Another aspect is that these aggregators are basically participating in the markets. They need a reliable way of ensuring that their investments are going to be successful. They have a very good idea about, like, for example, their economics in terms of participating in markets, but they have less view of the distribution system. So they might be overestimating how much services they can provide the bulk power system. And that's going to be a financial economic risk for the aggregators. And at the same time, the customer is another stakeholder in all this. And as mentioned before, the aggregation of the customer resources has to keep the comfort level of the customer in mind. So basically, as the VPPs, for us to make VPPs operational, we have to basically meet the needs of the distribution system reliability and economics of the aggregators and the customer comfort in mind. So, so how do we do all this? So basically, VPP components and interfaces are many, and they basically, they basically go from bulk power system all the way to customer. We have various systems in place on the transmission, such as energy management system that basically operate the transmission system. We have a similar system on distribution system called ADMS. And these are the existing systems, but for the VPP to take off, we need to implement new technologies, such as various forms of DERMS, the grid DERM, which is a grid-facing component of DERMS, as well as utility aggregator DERMS, which is really the aggregator or customer-facing aspect of DERMS. And it kind of functions as aggregator of aggregators, making sure that all the various aggregators are coordinated, and it's the holder of basically a capacity metrics, including all the DERs. So as we can see, there's a lot of systems in play and a lot of interfaces. And the main question is, how do we slice and dice all these functionalities in a way that it enables the the virtual power plant, but also, preserves its robust control and resiliency. And this is one of the challenges of implementing a VPP, and DOE and PNNL have done great work in defining some of the principles and requirements of grid architecture. And one of the concepts that has been very useful for us in industry is the federated or hierarchical control, where each layer is kind of decoupled from its upstream and downstream layer in terms of functions, so that all the complexity is hidden in each layer. So basically, each layer tries to meet the needs of its downstream devices while providing services to its upstream device. Another thing that I would kind of point out is the interaction between grid terms and aggregator terms. The grid terms does have access to the as operated model through either independently or through ADMS. So it has the visibility of the grid. However, the utility aggregators do not have this visibility. They have some sort of information and knowledge of the grid topology, but they don't have the visibility into the grid. So the data exchange and interoperability between grid terms and aggregator terms is going to be very important to enable virtual power plants. And we feel like there's a lot more that the R&D labs and industry can do to enable this interoperability. Another last thing to mention is the cybersecurity requirements. Still, a lot of the OT systems in various utilities are implemented on-premise, and so implementing aggregator terms in cloud requires the on-premise systems to interact with cloud-based systems, and there's some considerations to make there, and kind of updating each utility's security requirements is required, as well as cybersecurity requirements of interfacing with end-use customers through internet-based protocols. So we also have to come up with robust cybersecurity provisions to interact securely with customer devices through these cloud-based OEM aggregators.
Thank you, Yashar, for that very interesting presentation. For more information about the GridWise Architecture Council, please see our website at gridwiseac.org. And don't forget to subscribe to our YouTube channel at the site listed. Thank you.